cohomology, theory and applications. Please.
Thank you very much, Svetlana, for the introduction. And it's my big pleasure and big honor to give a talk at the conference dedicated to Viktor Matveyevich Buchstaber and his birthday. Unfortunately, I couldn't attend in person, but I have been staying with you virtually all these days. So today I'm going to talk about the results of our joint projects with A.Bahri, T.Panov, J.Song, and D.Stanley. The key player of today's lecture will be polyhedral products, and in particular, the moment-angle complex or simplicial complex. It was already introduced and discussed in several presentations during the conference, so let me just fix the notation. If K is an abstract simplicial complex, it has n-1 as its dimension and m as its number of vertices, then we can form the building blocks, the bricks of this polyhedral product from the pair T2S1. And the union of these bricks, building blocks of the construction, gives us a certain cellular space, a CW complex, ZK, which is, by its definition, always a CW subcomplex in the polydisk, the unitary polydisk in complex space C to the power m, where m, again, is the number of vertices of the simplicial complex. So instead of D2, S1, you could use possibly any topological pair of a set of topological pairs XA. This will give you polyhedral product in general. So in this talk, I want first to discuss the construction of double homology and cohomology of this object of moment-angle complex. And this actually is a very recent theory. It appeared in the framework of our project. And now it is studied in different papers devoted to toric topology and its applications. So at the end of my talk, I will also cover some recent results, some recent developments of this theory. But we start with this classical result of toric topology, the Buchstaber-Panov theorem, which says that we can compute homology or cohomology of this moment-angle complex with actually arbitrary coefficient ring with unit. But in this talk, I will use either integer coefficients like here in this slide or field coefficients, although it can be easily generalized to more or less arbitrary commutative ring with unit. So anyway, if we have, let's say, integer coefficients, then to compute homology of moment-angle complex, all what you need to know is all homology, simplicial homology groups of all full subcomplexes. K subscript capital I means you restrict simplicial complex to the vertex set capital I, which means you consider only simplices on the vertices from capital I. This is called full subcomplex, and you have a direct sum of reduced simplicial homology groups. Well, you can, of course, for any capital I and for any integer p, you can have an induced group homomorphism with respect to the inclusion map. For each j not in I, you obtain this homomorphism of abelian groups, and you sum up them then. It's an algebraic sum depending on certain signs. Epsilon ji means -1 to certain power, which is simply a sign. And if you consider this, this gives you a differential on the direct sum. And actually, this gives you differential, which we call D prime, on the right-hand side of the famous Hochster decomposition. So the right-hand side, the direct sum of reduced simplicial homology or cohomology groups of full subcomplexes is nothing else but the right-hand side of Hochster result, which describes Tor algebra of simplicial complex K. But I will also discuss it a bit later. Now, this is first geometric construction of differential D prime. Here it is. And this is taken with -1 to the power p plus 1 because later on we wanted to rely on this nice bicomplex relation. D and D prime anti-commute, where D is the ordinary simplicial boundary. Then you can also produce in a similar way cohomological version of the previous construction. Let's say you have Ki as a full subcomplex as before, and you consider inclusions of Ki deleted one vertex. This will also give you induced abelian group homomorphisms, and you produce alternative sum, which is also by hand checked that it also is a differential, d prime squared equals 0. And so this differential actually acts on what we call the right-hand side of Hochster decomposition, on the direct sum of all simplicial cohomology groups of all subcomplexes. And so by Buchstaber and Panov theorem, this gives you a differential on cohomology of moment-angle complex Zk. And the cohomology of Zk, by their result, is not only graded ring, but actually it's bigraded, or let's better say even multigraded ring. So differential respects 2 degrees by degrees. And our first definition is that the double cohomology of moment-angle complex is the cohomology of the cohomology. So we have ordinary cohomology of Zk. We just described differential D prime. And so with respect to this D prime, we can compute double cohomology. So this is the definition. This is the first one, the geometric one. And as I mentioned in the abstract, we are going to discuss 3 equivalent definitions. So this one is, let's say, geometric. And we turn now to algebraic description. The algebraic one also uses Buchstaber and Panov theorem and what is called Koszul resolution or Koszul complex of phase ring. So Zk is a monomial ring. It takes polynomial ring in M generators of degree 2. Remember that M stands for the number of vertices in K. And we consider quotient ring by the monomial ideal Ik generated by monomials in which indices form a non-simplex of K. So if you consider monomials indexed by non-simplices of K, you factorize and you obtain a monomial ring, which is called Stanley-Reisner or phase ring of K. So again, coefficients now are integers, but you can easily generalize it to more or less arbitrary commutative ring with unit. And here we prescribe certain by degrees to our generators UI, standing for generators of exterior algebra, and VI standing for generators of the Stanley-Reisner ring. And with these prescribed by degrees, you will have the above algebra isomorphism or ring isomorphism proved by Buchstaber and Panov. And now in this algebraic setting of Koszul graded algebra, by graded ring, we can define a new differential D prime acting on this Koszul ring by these simple formulas. UI goes to 1 and Vj goes to 0. Then you get by Leibniz rule D prime on all monomials with respect to UI and Vj, and then you extend it by linearity to all the Koszul ring. You obtain differential, so of course D prime squared equals 0, and here is the explicit formula which shows how D prime acts on any abelian on any module generator. So this is a simple formula, and you see again there is the same sign epsilon, which you already saw in the first slide, and this is actually this makes deep sense, because actually these differentials from these two constructions are closely related. Here is the first result that says that with respect to these two differentials, D and D prime, defined above on the Koszul ring. We have a bicomplex, so the anti-commute. This can be checked by hand. And moreover, we can consider the double cohomology, the first double cohomology of the bicomplex. And we proved that it actually is isomorphic to the double cohomology of the moment angle complex defined geometrically. So this provides second description, the algebraic interpretation of double cohomology. This says about first double cohomology and the second double cohomology. So if you reverse D and D prime in this cohomology setting, then you will obtain 0. It means you get first spectral sequence of the bicomplex, and it has the term E2, which coincides with double cohomology of ZK, and it converges to 0. So it has some non-trivial higher differentials, and they correspond actually to cohomology operations on ZK, which is another direction of further investigations. Recently, Steve Emelet and Ben Briggs published some paper about these high operations. So this bicomplex actually leads to interesting higher operations, higher cohomology operations of ZK. But anyway, this bicomplex is very interesting, and it gives you that the double cohomology is actually a graded, better to say even bigraded commutative algebra with the product induced from the ordinary cup product on cohomology product on ZK. So this is a graded commutative algebra. We can now ask how to commute it effectively, and I will later discuss some computations of this algebra. And moreover, with this result, we can say that the double cohomology also provides a new combinatorial invariant of simplicial complex K. And in fact, in the end of my talk, I will say a couple of words about applications of this theory to combinatorics and to topological data analysis. So in combinatorics, you will see some first applications, and they rely on the fact that it's a combinatorial invariant of simplicial complex K. So this is the theorem, the algebraic description. And finally, the third, I call it topological description because it arises from a fact that we have a space with a circle action. Actually, from the definition of ZK, you saw that the big torus Tm coordinate torus acts coordinate wisely on the elements, the points from moment angle complex. And you can restrict that action to a circle action. Now we will say a bit about what circles we are taking, but in general, if we have a circle action on a space, then you have it from, let's say, Kunert theorem, that the description of cohomology of the direct product S1 times X. And this is the well-known formula. And the right-hand side includes the so-called derivation. This is a nice operator on the cohomology of X. So in the terms of this derivation, we can easily describe what our differential D prime is. Namely, if we consider the action of the east coordinate circle on moment angle complex, then the derivation corresponding to this action will be induced by the derivation of the original chain complex or Koszul complex, better to say, given by the simple formulas. This derivation acts on generators of Koszul ring as follows. Uj goes to the Kronecker delta and Vj goes to 0. So these formulas actually imply that the derivation corresponding to that diagonal circle action on the moment angle complex coincides with the differential D prime defined above. This holds because derivation corresponding to the diagonal circle action is just the sum of derivations corresponding to coordinate circles. So if we prove the first formula, then the second part of the theorem implies. But how about the first one? Here is a simple proof. So actually we can interpret the coordinate circle action on moment angle complex in terms of a map of just two moment angle complexes. To do this, we consider the left-hand side of this map, the domain, as a moment angle complex with one ghost vertex, let's say I prime, which corresponds to I. This is a ghost vertex of the left-hand side. And it's easy to see that this circle action is nothing else but the induced map of moment angle complex. So actually that is a functor in a sense that if you have a simplicial map of simplicial complexes, it induces an equivariant map or continuous map of moment angle complexes. So this fact is used here. We interpret it as a map induced by a simplicial map of complexes. And the latter simplicial map corresponds on the level of, let's say, Koszul rings or Koszul complexes to the following nice maps. This map on generators is defined as follows, as is written here explicitly. And from these explicit formulas, you see that the derivation of UI U or Uj is just Kronecker delta. So from the right-hand side of these equations, and Vj goes to 0, there is no second sum, and so it goes to 0. Now this is proved. Now this is proved. So we have these three equivalent constructions or definitions of double cohomology, and it's time to compute something. And maybe the very first example in toric topology is just a simplex and the boundary of a simplex. So what about a simplex case? If K is a simplicial complex without ghost vertices, we can characterize the case of a simplex as follows. So a simplex corresponds to the simplicial complex for which all full subcomplexes are acyclic. This is first. And in this case, Zk is just the whole unitary polydisk, as we discussed previously. Zk is acyclic. And it's interesting that only in this case, the rank of double cohomology is equal to 1. In all other cases, it equals to 0, because actually the Euler characteristics, the Euler characteristics equals to 1, and in all other cases, the Euler characteristics equal to 0, because actually the Euler characteristic of ordinary cohomology equals 0. So this follows. And slightly less trivial, but still very handy example is that of boundary of a simplex. So for arbitrary boundary of a simplex, you just have d prime equals 0. And d prime equals 0 on ordinary cohomology means that double cohomology must coincide with ordinary. So in this case, like in the previous case, the double cohomology coincides with the ordinary, and here are generators. Well, if we proceed with, let's say, polygons, then we have more or less complete answer. We can compute double cohomology. Here, example of fogon, or boundary of a square. Actually, it's a join of two disjoint points together. And we know the topological type of moment angle complex is S3 times cross S3. And in this case, actually, well, from the previous double cohomology of 2 points equals ordinary cohomology corresponding to 2 points. Here are generators of the ordinary cohomology groups coming from Buchstaber and Panov theorem. And moreover, you easily see that the induced differential d prime is trivial again, like in the previous case, which immediately implies that, again, double cohomology coincides with ordinary. Moreover, it's interesting to note here that double cohomology is just a tensor product of double cohomologies of these spheres, of these moment angle complexes corresponding to elements of this join, K1 and K2. And actually, this can be generalized. So this is maybe first general result today. The first general result about computation of double cohomology says that under some technical restriction, namely ordinary cohomology of Zk and Zl must be projective over the coefficients, then you can prove that the cochain complexes, which are just ordinary cohomology of moment angle complexes, you remember, it's isomorphic for the join. It's isomorphic to the tensor product of these cochain complexes. So it immediately implies that if you consider double cohomology, it means isomorphism. In case, let's say, in case of coefficient field, one immediately obtains that double cohomology of moment angle complex corresponding to join, which is actually homeomorphic to Zk times Zl, to the Cartesian product of moment angle complexes, and this is analog of, let's say, QNet formula or something like that. And the same statement actually holds for double homology. So this result, together with previous computations, allows to obtain double cohomology of rank 2 to the power n. Let's say a bit more about boundaries of polygons. So if you have a pentagon, here is again description of generators of ordinary cohomology of Zk. And here, unlike the previous situations, we understand that we have a one non-trivial differential d prime between -2, 6 and -1, 4. So we need to compute kernel and co-kernel. And to do that, we consider generators, of course, coming from the algebraic description, coming from Koszul ring. And this is the corresponding matrix of this operator d prime. And actually, it has rank 4 and defines a homomorphism onto direct summand of Z5, which gives you the ranks are equal to 1. And so these groups are non-trivial and isomorphic to Z. And all other bigraded double cohomology vanish. So in particular, they do not coincide with ordinary, because in ordinary case, Betty numbers 3 and 4 are equal to 5. This is connected sum of sphere products. So this is the first case, maybe when they are not equal in polygon case. And here is again a general result that we proved for all polygons. If you have an m-gon with m greater or equal to 5, then double cohomology has rank 4, and it's non-zero only in bidegrees, which you can see in this slide. All other bidegrees vanish. And in this bidegrees, it's just of rank 1, it's just Z. So, of course, it's quite absolutely different from the ordinary cohomology of moment angle complex for a polygon, which is known from McGovern's work and Bossier-Meresman. And here is maybe also one generalization of the previous computations coming from, let's say, homological algebra. So for arbitrary Gorenstein complex with field coefficients, we can consider double cohomology of Zk, and it turns out to be a Poincare algebra. So in particular, if K is Gorenstein star is equivalent to that condition that link of any simplex in K is a homology sphere of the corresponding dimension. This is Gorenstein star, and Gorenstein complex is just a join of simplex and Gorenstein star. That's an alternative description. So for Gorenstein star, for this homology sphere, and all links are homology spheres, then you have this Poincare algebra, and you have this, let's say, additive Poincare duality or symmetry of bigraded Betty numbers for double cohomology. Well, actually, there is Avramov-Golod theorem in commutative algebra, which says that Tor algebras of Gorenstein complexes are Poincare algebra. So actually, Tor algebra is Poincare algebra if and only if complex is Gorenstein. So Avramov-Golod theorem is if and only if. Here we have only one direction. So our question is, can we prove that the opposite implication holds? That's an open question. So can we characterize Gorenstein complexes as such that double cohomology is Poincare algebra? Now, okay, so double cohomology also can have arbitrary torsion. At least we can take minimal triangulation of RP2. It has 6 vertices. And here you see the result of explicit computation of certain bigraded cohomology groups. You see that 9-dimensional double cohomology is isomorphic to Z mod 2. So it has 2 torsion, as in the ordinary case, in the case of ordinary cohomology of moment-angle complex due to Hochster decomposition. However, we see that the torsion part, which is in dimension 1 in homology, of course, it vanishes in double homology of moment-angle complex. So this also is surprising a bit, and also it shows that the usual universal coefficient theorem fails in general for double homology cohomology. So this example is really tricky and inspiring. Well, a bit more general results. So this general result, we call it gluing theorem. It says that actually most of double homology or cohomology vanishes if we glue a simplex to an arbitrary simplicial complex along a face. So whatever K prime was, if you glue a simplex to it alongside its face, then the double cohomology of what of K is Z plus Z in by degrees 0, 0 and -1, 4. So actually, this shows that for, say, let's say, discrete set of points, always it's Z plus Z, unlike the classical case in which, for example, here for 3 points, it's just a wedge of spheres. And of course, Betti numbers are different. It's not Z plus Z. So again, it's different from the ordinary cohomology of ZK. Using this very nice general setting, we can easily prove the following theorem, which says that we can compute double cohomology in the case of flag Golod complexes, which is known in toric topology from the works of Garbich, Panov, Theriot, and Wu. We can describe a certain big class of simplicial complexes in these 3 equivalent ways. So this class consists of simplicial complexes obtained from a simplex by gluing simplices 1 by 1, starting with a simplex. So it's a class of flag simplicial complexes with chordal graphs. And moreover, it's equivalent in the flag case to that case homotopy equivalent to a wedge of spheres, and it's equivalent to that case a Golod complex. And where we apply the previous result is the last item, which says that it is the case when double cohomology is Z plus Z in the corresponding degrees. Well, finally, let me show you the example which says that if you take something different, which is 2 boundaries of triangles glued in a vertex, this does not belong it's not covered by previous general results. And you can also compute explicitly the ordinary cohomology groups first, and then you get the cochain complex for the double cohomology. And when you compute the double cohomology, you arrive at the same result, Z plus Z in this by degrees. So of course, it's challenging, and we want to ask, if possible, to characterize the simplicial complexes such that the rank of double cohomology is given positive even integer. So even in case 2, it's not clear. I will say in the next slide about it, but it's not clear how to characterize. Now, recently, Han gave an example of rank 6. So together with the previous computations of joints, it gives you this exponents for constructible ranks. but for all other ranks, it's an open question. And two applications. First application is combinatorics. So we call simplicial complex wedge decomposable if it can be written as a union of two simplicial complexes glued along a proper face of both. For example, in the language of graphs, it is called a clique sum of two graphs. It's known in graph theory. And using this double cohomology, Ruiz and Stanley this year showed that all wedge decomposable simplicial complexes have double cohomology z plus z, and by degrees 0, 0 and -1, 4. So they actually generalized our gluing theorem for the case of simplex. So actually, our conjecture now is that for any connected simplicial complex, it's wedge decomposable if and only if this computation, this general result holds. But so opposite direction is open problem. The very final thing is application topological data analysis. It's just as a remark, and for those of you who are interested in TDA. So in one of our two projects, we actually defined a new barcode of data set based on this double cohomology. First, we did it actually for the classical homology of moment-angle complex, and it turned out to be not satisfying the stability theorem. Unfortunately, this is not good, and so it actually motivated our research in double homology and cohomology. And with this research at hand, we were able to prove stability theorem holds for bigraded double persistent homology barcode. So if you have two finite pseudometric spaces, then you can define persistent double homology using the properties of double homology for moment-angle complexes. And you can prove that interleaving distance between these two persistence modules is always less or equal to 2 times Gromov-Hausdorff distance between these two pseudometric spaces. Actually, using isometry theorem with field coefficients, you immediately obtain the corresponding inequality for bottleneck distance between the bigraded double homology barcodes. So this is our main result in applications in TDA. So these are just references. The first and fourth are the papers we uploaded to the archive, and one of them is already published in the frame of these projects. And there are also applications papers and the fundamental monograph by Viktor Matveyevich and Taras Evgenievich. So thank you very much, everyone, for your attention. And I want to say happy birthday and all the very best wishes to our dear Viktor Matveyevich. Thank you again.
Thank you. Are there any questions? Remarks? Okay.
Vanya, it's Mitya.
Oh, yes, Mitya, hi.
Hi. What can you tell us about the double cohomology of complexes which are triangulations of a two-sphere? Maybe something is known about them.
Of two-dimensional.
Of two-dimensional sphere, yes.
Well, actually, we do not have any particular results, but it turns out from our general results that it's certainly a Poincare algebra, the double cohomology. And in certain particular cases, perhaps we can say we can get computation using these techniques of the algebraic description, for example. So we can do it by hands. But unfortunately, this story lacks explicit formula, Like we do not have anything comparable to Buchstaber theorem formula. So unfortunately, we cannot generalize it so far. So for polygons, we have a general result, general answer. But even for three-dimensional polytopes, and of course, for two-dimensional simplicial spheres, the same, we do not have a general result. Only Poincare duality algebra, so you have this symmetric Betti vector, Betti numbers. And basically that's it.
And polyhedrality is for triangulations of any dimensional sphere, yes?
Yes, exactly, because any triangulated sphere is a Gorenstein star complex. And for all Gorenstein star, you have that it's Poincare algebra.
Okay.
It's a general result, yeah.
Okay. Thank you. Thank you.
Yeah, thank you for your question.
I got a question. If you know why the stability theorem just fails for the just ordinary cohomology of moment-angle complex.
Yeah, sure. So the main point is that actually we work with pseudometric spaces, and you can have a situation when the distance between 2 points in the data set is considered to be 0. So in this case, you know what happens with the corresponding Vittori-Rips complexes. There is certain operation called doubling of a vertex. We also described it in our paper. If you are interested, you can have a look at that paper in the archive, our most recent one, where we deal actually with topological data analysis. And actually, this doubling operation changes the ordinary cohomology of moment-angle complex. But from the Gromov-Hausdorff viewpoint, the Gromov-Hausdorff distance between x and x plus such a point in the zero distance is 0, of course. So, so right-hand side of your stability theorem will be 0, and left-hand side of your stability theorem will be positive, non-zero, because we deal with barcodes corresponding to ordinary moment-angle complexes, and Betti numbers will grow if you have a vertex on 0 distance. So this fails because of that. Left-hand side is positive in general, and the right-hand side is always 0 because Gromov-Hausdorff for these 2 spaces is 0. However, we proved that for double homology, when you compute the corresponding barcodes, the distance will be 0. So actually, this problem disappears for double setting, for double homology. Yeah, the problem of 0 distance point, the point in 0 distance, because it's pseudometric space. In metric spaces, perhaps it works, although we didn't check it explicitly. But anyway, we worked with pseudometric spaces. Yeah.
Thanks.
You're welcome.
Any other questions? If not, let us thank the speaker again.
Thank you very much.
Ваня, ты меня слышишь?
Да, Виктор Матвеевич, слышу
Можно.
вас.
Thank you very much for your talk. It was for me a great pleasure to see you and hear about your result and result of your colleague, and only a few comments.
Yes.
Maybe we discuss this with Taras. When somebody see double cohomology, 3 cohomology, arise immediately idea, maybe a functor, and you obtain like Atiyah-Hirzebov spectral sequence, which start with usual cohomology, and the higher differential give to you next step. But what we have in have moment-angle complex ZK.
Yes.
But you can consider equivariant cohomology vibration.
Right.
Has M hyperplanes, facets. So you have base CP infinity in degree M, and fiber exactly ZK.
ZK.
So
yes.
you can consider the what kind of Oldenburg-Moore. Of course, you know what is mean.
Yeah.
Oldenburg-Moore spectral sequence, which start with space to compare your calculation and compare, we obtain certainly, I understood your example shows us it is a new result, but
Right,
certainly
yeah.
interesting to apply Olberg-Moore spectral sequence of fiber. That case, cohomology of ZK.
Yeah.
Can you and your colleague compare? Because it shows that homotopical invariant. Of course, it is not a new cohomology theory because it is, it is cohomology, not usual cohomology, because equivalent cohomology. So, thank you very much for your talk, for your result, and I will be happy to continue our conversation.
Sure. Thank you so much, Viktor Matveevich, for your comment and suggestion. Definitely, this is can be a new direction in the framework of that projects, and we can certainly continue that in this direction you suggested, you proposed. Yeah, I'll be very happy to continue our discussions on this and all other related topics. Certainly. Thank you so much, Viktor Matveevich, and happy birthday again.
Let me say a few last words, because trust me, so I am happy to see all you, because it was the last talk. We stay 1 week. It was not so simple, it was heavy, but we survived. And I think this is the best present for me. All to be healthy, powerful in mathematics, and I am sure that we will together will be in contact and obtain the pleasure for our discussion, for our meeting, and thank you very much for all. Thank you very much.
Okay. Someone else would like some concluding remark?
Okay. Thank you. Yeah. All right. Once again, thanks everyone for taking part in this event. And once again, happy birthday to Viktor Matveevich. And I very much hope that we meet again soon on many other occasions related to Viktor Matveevich, 85 years with 100 years. And we also have a possibility to welcome Viktor in person. And of course, yeah, so let's all the best and many more fruitful years, many more conferences and beautiful talks and beautiful results. And of course, great happiness and long life is full of mathematical results. And yes, please. And yeah, thanks everyone for joining us, and thanks all the speakers for these talks. And we hope we can meet again on some other occasion. Thank you.
Of course, as a speaker and as a participant, I'd like to thank very much organizers, right? Of course, please stand up. And Sasha, Taras, no, please. Thank you. Right. No, you, please. So let's thanks the people who made this possible, and I enjoyed thoroughly the event. I mean, it was so great, and many thanks to Viktor Matveevich, of course.
Thank you. Thank you. Thank you. Thank you.
Thank you.